I am Russ Taylor, by the way. It's really great pleasure to introduce Cenk Cavusoglu, who he got his PhD in 2000, spent a couple years at Berkeley, I guess as a postdoc, and then moved to Case Western, where he has been doing really very, very interesting work. He's now a professor there, and why don't I shut up and let's listen to what Cenk has to say.
Thank you very much, sir. Thank you very much. So today I'm going to talk about our kind of recent research on basically trying to build task automation in surgical robots, kind of basically towards the goal of realizing intelligent robotic surgical assistance. So I first want to start with acknowledging kind of the people who worked and collaborated with on this project. So some of the work that I'm going to talk about has been kind of proposed and done in collaboration with Wyatt Newman from Case Western, and Ken Goldberg, Peter Abil from Berkeley, and Ron Alterowitz from North Carolina Chapel Hill, and my students kind of who spent their kind of years working on this research. So for just as a kind of introductory step, so for robotic surgical systems, so there's basically three paradigms that the physician interacts with the robotic system. So at one extreme, kind of we have the teleoperated control, where kind of basically the robot is an extension of the surgeon, but basically the tool and the handle are separated, and basically the robotic system is basically controlling the robot, and the robot is acting like a slave to the physician who is controlling the robot through a master device. Kind of there's this, the shared control approach, which is kind of where the robot and the surgeon kind of grab the same instrument, where the robot is basically is assisting the physician by kind of enhancing their capabilities, right? Maybe stabilizing their motion and aiding in performing tasks, kind of introducing guidance. And then at the other extreme, there's the supervisory controlled approach, where kind of the physician kind of sits and programs the task that needs to be done, and then kind of the robot goes down and executes the task under the physician's supervision. So this scheme is kind of used more in image-guided applications, kind of where you work with your large amount of preoperative data, whereas the teleoperated control approach is kind of where you are working in unstructured environments, like in open surgery, or not in minimally invasive surgery, kind of where you are doing really complex manipulations with deformable objects. So for my focus is on basically trying to take this teleoperated paradigm and try to move it towards the more supervisory control approach. So with the teleoperated surgical robots, the state of the art kind of can be observed through the Da Vinci system by Intuitive. So it is basically a tremendous improvement over manual performance of minimally invasive surgery. Kind of we have the 6 degrees of freedom manipulators, which have improved dexterity. There's immersive interfaces, which improves the hand-eye coordination. And then kind of once we have a platform like this, then it opens door for information augmentation, that you can introduce data, alternate imaging modalities to the physician, and with just-in-time information. But there are still some existing shortcomings kind of with this paradigm. First of all, the tasks are still slower than open surgery. I mean, that's kind of much faster than kind of manual, minimally invasive surgery, but still, we are not at the level where kind of the system, the physician can perform these manipulations at the speed that they could do in open surgery. And there's this, with the state-of-the-art systems, there's still the lack of high-fidelity haptic feedback, which is kind of part of the reason why the tasks take longer. Also, kind of because of the nature of the interface and also because of the nature of minimally invasive surgery, there's still issues remaining with situational awareness. And then kind of when this for surgical robotics, especially the robotic surgical systems were starting, kind of one of the pitches was, well, we can do remote surgery. We can do surgery in the battlefield, in the rural areas. But the technology is still not, that we are far from doing that. I mean, there were some demonstrations, but I mean, there are some fundamental limits with time delay teleoperation, which kind of makes this kind of remote surgery impractical. So with our kind of focus has been trying to basically make the robot less like a slave, more like an assistant. So we want to basically provide robots with low-level task automation capabilities. So then the surgeon will be able to interact with the robot at a higher level than kind of basically directly controlling through teleoperation. So this way the system can assist the physician in basic manipulation tasks, kind of like retraction, dissection, exposure, suturing, and then kind of this way we can reduce the tedium of simple repetitive tasks. And then basically the robot can assist with the complex manipulation tasks, and we want to reduce the cognitive load and basically have the physician focus on what they are best at, which is kind of basically using their brain to think and plan and kind of be aware of what is going on and perform the complex manipulations. So, I mean, of course, this is a kind of a big goal. So our focus kind of when we started this research was basically to focus on basically doing these low-level surgical manipulation capabilities for delicately formed objects and to demonstrate that, okay, the feasibility of this and kind of try to start a roadmap. Okay, what are the problems and what can we do? What are the potential solutions? So for when we started this research about 4 or 5 years ago, we said, okay, we are going to look at 2 simple tasks which are common in surgery. One was retraction, because it includes key skills and algorithms for manipulation of deformable objects. And then the second one is basically surgical suturing and knot tying, basically because this is arguably most complex dexterous manipulation by manipulation in minimally invasive surgery. So these were the 2 tasks. Now, if you want to do task automation in these tasks, okay, well, then this comes back to kind of the traditional robotics problems. Okay, it's planning, control, perception. Okay, so and then for perception, there's this, you need to do perception for control, kind of with high speed, and then you need to do perception for planning so that you can give high-level information about the scene, about the task. So then kind of within this context, again, this is kind of what I have top there is the robotics itself. So now we said, okay, we started with, again, smaller problems in here that I'm going to go over. Again, since we don't have time, it's just going to be giving the highlights of kind of what we have been doing and where we are going towards. So the projects that I'm going to talk about is going to span kind of all 3 areas a little bit. So I'm going to look at perception for planning, which is where the goal is to estimate deformed object boundary constraints and the material parameters for manipulation. I'm also going to show some results from kind of perception for control, where the focus is on localizing and tracking kind of surgical threads, which is an important piece of the puzzle. So I'm going to talk about a little bit of planning that we have done, where with kind of needle pad planning and then kind of needle grasp planning and entry port planning. And then finally, I'm also going to show some things about the control, where we were doing kind of needle driving and knot tying. Okay. So first, perception for planning. Okay, the motivation. So first of all, kind of in these advanced algorithms that kind of people have developed for kind of planning manipulation of deformable objects, kind of they are basically model-based. And the problem with these model-based approaches is that they depend heavily on these models, depend very heavily on the knowledge on the boundary conditions and to some extent the material properties, right? So kind of the way an object deforms, it's very heavily dependent on kind of, okay, where is it anchored in space? Okay, is it connected to this organ or is it touching this surface? But the problem is in surgery, the knowledge about anatomical configuration is very limited. So you can say that we are going to get preoperative imaging, but things shift in the surgery, and there's the kind of subject variability, intra-subject variability, and also we are changing the environment where you are manipulating. So, and these are sometimes in unpredictable ways because you are cutting, but you don't know how well you cut. So our approach has been to look at this problem was basically the first focus on boundary constraint identification and active exploration, and then kind of secondly on estimation of the mechanical parameters of the tissue from the manipulation data. So for the boundary constraint identification, so kind of the basic problem setup looks like this. So kind of there's this object, okay, and then we assume that there are some features on it that we can track over time. Okay, so that's the kind of vision problem, which, okay, unfortunately is not my expertise. So I kind of said, okay, well, assume that there are these features. And now my problem is that there's this part of the boundary which is anchored, and I'm trying to identify that. I don't know what is anchored, and I assume that I cannot really figure that out purely by looking at it. So I need to start manipulating. So, and then kind of the robot moves, and then we can track these features. So then the idea is, then you can basically says, okay, I'm going to do the manipulation and I'll have a model and I'm going to generate hypotheses and to see which hypotheses agree better. So the part of the problem is that kind of, again, the models that are typically used are very computationally intensive. So you don't want to just run finite element simulations with hundreds of different hypotheses. And this is not like the traditional SLAM problem where checking for individual hypotheses is easy. In here, checking for hypotheses is difficult, it's time consuming. So then kind of you basically need to do kind of smart ways of to basically figuring out which part of the state space that you need to explore and kind of you can say that, okay, well, can I use multi-resolution approaches and so forth. But basic idea kind of that we pursued was to use an approach which is inspired by these kind of occupancy grid-based algorithms, mapping algorithms from mobile robotics. So we basically do a hill climbing, we try to figure out what is the minimum number of changes that I need to do to the boundary condition hypothesis that will explain my observations. So that's the premise. And then we can basically use this, the maximization of this agreement. So, but then the problem is for a problem like this, it's like in any identification problem, what you can identify depends heavily on what is the input that you are giving to the system. So then the problem was, okay, we can do some manipulations, but we might not be able to figure out from, like I say, naive manipulation, okay, what is the boundary condition. So then the problem comes down to, okay, what is the it turns into an active exploration problem. So what is the right motion that I should do in order to separate my hypothesis as much as possible so I can identify which one is right. And in this case, okay, then we can basically take the basic algorithm and apply kind of use the probabilistic interpretation. So which then you can assume some probability density on the observations, and then you define your beliefs. And you can then basically do information maximization to find out, okay, what is the right motion to separate your hypothesis. And then kind of you have this, you do the exploration, kind of robot performs the motion, you get data, and then you run your identification, you update your hypothesis, and then you go back and go forward. So we performed some experimental evaluation of this, so I'm kind of running a little slower than I was expecting. So, so for then, the next step is to do parameter estimation, but it turns out that the boundary condition estimation is very robust to tissue parameters, so you can basically, once you figure out the boundary constraints, you can go back and use the same data to determine the tissue parameters. And in this one, kind of, you basically use an inverse finite elements approach. So again, it's in the same spirit. You have your hypothesis, you run simulations, and then you figure out, okay, how well do they match, and then how should I change my parameters in order to agree with the data. Now, with the given boundary conditions, now your problem is much easier, and then you can get effective solutions. So again, not much to show. Kind of we did experimental evaluation, and it turns out that actually we can kind of pretty reliably, kind of within a reason that we can estimate these parameters, which is kind of then good enough for the planning application. So the second part is that I want to talk about is perception for control. So here, so again, for when you are doing a manipulation task, you need to know kind of what is where, right? So, and the problem is, like for example, when you are doing suturing and knot tying, there's a deformable object around, which is the loss of uncertainty, and you want to basically localize it where it is, and then you need to track in time. But since now this time the problem is part of like a perception for control, you need these computational efficient algorithms, and you don't want to rely on a priori knowledge of the system about the parameters. And you want to basically, but in this vision problem, you want to handle this complex topologies, like when your thread is overlapping and crossing over, and if you have a knot. Okay, so let's see if these are running. So in this approach, can be basically used, again, take advantage of the supervisory nature of the paradigm. So the physician basically selects the thread that they're interested in, because there might be multiple things. So kind of we take help from the physician. They kind of click on, okay, that's the thread that I'm interested in. That's the one that I'm going to do manipulation. So, and then kind of deformation we model as a NURBS curve. And then kind of basically first do any segmentation. You do a kind of a thin feature identification algorithm. And then kind of basically kind of you construct a 3D model in space. And then you basically, you are using stereo vision, you basically project it onto the two images. And then you do basically energy maximization based approach. And then you project it back to 3D. And then you basically go back and forward. And then you basically take advantage of the three-dimensional information, so you can basically use that to resolve cases when you have kind of overlaps. And then there was a kind of one demo where we have actually, you can actually track a knot too. Kind of why kind of surgeon kind of creates a loop and then pulls and a knot occurs. So, and then again, kind of we can perform this tracking in real time. So now another part is kind of about the planning. So we want to, for example, for needle driving, we want to minimize the interaction forces with the tissue. But the problem is kind of when we are doing this delicate manipulation with the tissue, kind of we have very limited sensory feedback. Okay, so typical, the conventional surgical robots that we have off the shelf, so they don't have force sensing. And kind of the vision is also, especially when you are manipulating, kind of you have occlusions and so forth, so you have limited sensory feedback. So you would want to do things as much as possible, kind of open loop, and get feedback kind of at the critical steps of the procedure. So kind of we basically created this approximate models of kind of needle tissue interaction, which is kind of very similar to, it's inspired by the traditional models, but kind of we need to do lots of simplifications in order to be able to run these algorithms in efficiently, so we can use part of the control loop. So we basically kind of had a big approximation here where we were really modeling the deformation of the tissue during this manipulation by using an FEM model, but we say, okay, the needle is moving, it is, assuming the tissue is not deforming, there's a volume of it that is being swept by the needle. Then that should relate to the interaction forces that is going to be generated by the robot. And then, of course, that's a big approximation, and you want to check if it makes sense, if it fits the data. And kind of we did simple experiments with the tissue phantoms, and actually we can show that we can estimate the parameters pretty well. So okay, I'm going to skip this part. Okay. So the next part of the problem is then, okay, you can drive the needle, then the needle grasps. Okay, so when you're performing the task in an autonomous way, so you don't want to use kind of a traditional like optimization algorithms that kind of people, or kind of needle grasp selection that you need to perform. It basically needs to focus on the pitfalls that are associated with an autonomous operation. So there won't be a user to correct the actions. And when the robot is going and grabbing the needle to perform the thread, then usually there's kind of imperfections in your needle grasp, and you're also imperfections in your calibration. So you want to eliminate kind of needs for regrasping the needle under these kind of imperfections in motion. And we basically kind of proposed this grasp and entry port selection algorithms, which focuses on robustness kind of uncertainties here. And then finally, we're looking at this autonomous knot tying, where again, the challenge is managing uncertainties. Okay, well, the thread moves, okay, we have some sensory feedback, but we want to basically manage uncertainties so that we can minimize reliance on real-time sensory feedback. And also take into account that there's this coordination problems with the two manipulators, because we don't want to assume a perfect calibration with the two manipulators. So the approach that kind of we took kind of in this problem was to basically use vision-guided control at key steps, and use basically specialized strategies kind of when you're tying a knot to reduce the controlled uncertainty. So we don't tie the knot like a physician does in open surgery or minimally invasive surgery. We basically do it in a way that the robot can do almost blindfolded. So you want to kind of basically keep the thread in tension or in mild tension at all times, so you know exactly kind of how the thread is going to behave, and then kind of take that into account, and also that you have a limited workspace, and you kind of manipulate the thread kind of carefully in a way that will kind of keep the uncertainties under control. And when there are uncertainties, like for example, when you are trying to grab the tail of the thread, which you are not holding, so then can you basically go back and say, okay, my vision algorithm, tell me where should I go and grab. And then with this one, I want to kind of say where the research is going. So again, the first step is further advances in task automation and kind of basically how we can perform more complex manipulation tasks and basically looking at effective user interfaces for enabling the physician to control. Okay. And I would like to thank our research supporters and basically my students and collaborators over the years. And perfect, 5 seconds to spare. So, thank you very much.
Hello. Good morning, everyone. My name is Tipakorn Graikan, and I will be talking about the other project we are working on at Case Western Reserve University. We are currently working on MRI actuated catheters for catheter ablation of atrial fibrillation. And my part in the project is motion planning. Okay. So atrial fibrillation, or AFib, is the most common cardiac arrhythmia. In AFib, electrical signals get transmitted chaotically, and that cause irregular heart rhythms. Okay. The standard treatment in AFib is catheter ablation, which creates non-conducting lesions around the pulmonary veins using catheters. We are currently working on a new robotic catheter system that uses MRI's magnetic field for remote steering. In the design, a set of coils is attached to the distal end of the catheter. Then the catheter is actuated by the cross product between that magnetic field and the local magnetic moments generated by the coils. And you can see the coils in the picture below. With this design, MRI is used for both visualization and actuation. Okay, in order to make motion planning tractable, the catheter is approximated by a pseudo-rigid body model, which is basically a set of rigid links connected by flexible joints. In this work, we have 3 orthogonal coils as our actuator. And since we can only produce torques on the plane that is orthogonal to the direction of the magnetic field, we essentially have only 2 degrees of freedom actuation. Then the problem is to have a good approximation of the catheter, we have to have relatively high order model, which makes our system under-actuated. But on the other hand, the surface we want to operate on is also 2-dimensional. So we can still solve the problem by performing motion planning in the task space, where the joint velocity is decomposed into tip velocity and internal motion. Okay, and we have some simulation results on ablation. If you'd like to hear more, please come to my interactive session. Thank you.
Good morning. My name is Arun. I'm going to be talking about estimating the shape of medical snake robots using Lie algebra. So at Carnegie Mellon, we have developed snake-like robots for minimally invasive surgeries. And it's very important for us to estimate the shape of the snake robot as it enters the body. And to do that, we need to develop filtering techniques which can accurately estimate the shape, which further means we need to estimate the position and orientation of bodies evolving over Lie group. The motivation for this work comes from the work of Chirik Jain and others, who look at bodies evolving in an SE3 space and look at its distribution. It looks like a banana, and approximating that with a Gaussian is not really a very good idea. So you instead fit a Gaussian to the spread in the space of its Lie algebra, and then map it back into the Cartesian coordinates, and that looks like a better representation of the distribution. So what we do is, the medical snake robot has a number of links, and each of these links evolve over the SE3. So we try to use the underlying structure of the Lie group and its algebra to come up with an extended Kalman filter to estimate the position and orientation of each of the links of the robot. So prior work by our group involved coming up with an extended Kalman filter framework where the state vector had the position of the links expressed in terms of its Cartesian coordinates and the orientation of the links expressed in terms of Euler angles. But in our current approach, we're trying to express the location of each of these links using exponential coordinates. And we also derive the process model and the measurement model in terms of exponential coordinates. So by doing so, what we obtain is a very good estimate of the shape of the snake. So if you look at the plots over there, the blue curve is the ground truth, and the green curve is the shape as estimated by our approach, while the red one is the shape as estimated by the approach which uses conventional parameterizations like Cartesian coordinates and Euler angles. We observe that the error is pretty low in our approach, the maximum error as well as the average error over all links. So yes, I would be happy to discuss more about this with you during the interactive session. Thank you very much.
Hello, my name is Jusok Lee. I'm a senior engineer at Samsung Advanced Institute of Technology in South Korea. The topic of my talk is modeling and controlling a single-port access surgical robot developed by our group. This is submit as well. With the advances in medical procedures and technology, surgeries are evolving to be less invasive. For example, single-port access surgery requires only a single incision made on the abdominal wall. Because incisions are minimal, patients recover faster with fewer scars. But there are challenges associated with smaller access for the tools. For example, payload and workspace are reduced. The picture that you see on there on your left, on your right, that's our prototype that our group has built to address those issues. We envision this robot entering the patient's body through a single incision and reaching various areas in the abdominal cavity for surgical operations. The robot has two arms, a camera, and a snake-like mechanism called the guide tube that guides the tools mounted on its distal end. I was supposed to show you a movie. Maybe you come to my interactive session, I'll show you a movie of that. The diameter of the guide tube is 3 centimeters, and the length of it is 25 centimeters when it's fully inserted. So that was the introduction that was just the introduction of my talk, and the main part of my paper is about controlling the system. First, we need to intuitively control the guide tube. To do that, we first obtain the forward kinematics model of the guide tube, and then calculate the Jacobian. Then we use a Cartesian level controller. And we have results for that. And secondly, we need to remove the backlash that exists in the tool joint. The backlash is caused by the inherent slack required in the actuating wires with additional nonlinear effect from the friction between the wires and the conduit. I don't think I have and we have a compensator for that. I think that's it. Thanks for listening. For those interested in learning more, please drop by at the interactive session. Thank you very much.
Hi, this is from Hamlin Center Imperial College. So this is the work by Ling Zhang, who is an MSc student from our group. Unfortunately, he didn't get the visa, so I'm here standing on his behalf. So what he's trying to do is really to provide a semi-automatic navigation system for robotic telecardiography using generalized shape models and also using RGBD cameras. So the basic idea is that in ultrasound that localization and all these things requires quite a lot of domain-specific knowledge. And using the telerobotic operation has certain advantages, particularly for remote care in battlefields and also in emergency. So the idea here is that can we provide something that is reasonably generic and also can cater for large-scale patient movement and so on. So this is really the motivation of this study. So the basic setup is quite simple using the KUKA robot, use the master-slave setup. And the idea is that you can remotely operate the robot, and here the main thing is to ensure consistent contact, the ultrasound window, and also that to cater for breathing and the respiration and body movement. So this is the system setup that, as you can see here from the slave side, we use two connect systems, so that give you an entire 3D coverage. Then this information is fed into the master side that they use Omega-7 to control it with haptic feedback. And what is done here is really to use the point cloud from the Connect, and also that use the shape modeling to cater for subject-specific anatomy and also changes in motion. So for those of you who are not familiar with statistical shape model, this in fact is very widely used in medical image computing. So the basic idea is that you have a population and segment, normalize, and to extract the principal modes of variation. So showing here, these are the three principal modes of variation that, as you can see here, one of which is due to respiration, and the other is due to abdominal motion, and so on. So with this, then you can cater for all the subject-specific changes. Then when you come down to organ localization, then you have much better view in terms of where to go and so on. So with the Connect information, you use ICP, co-register. Then with this, then you can cater for all the things that you want to do. So this demonstrates how do you cater for large displacement as well as respiration and so on. So all these are in fact very important that for emergency or battlefield and or remote operation. So here are some further examples and to demonstrate how it works. So if you want to see how the system actually works and some of the specific issues we need to address, then I'll be very happy to talk to you on his behalf during the session.
Good morning, everyone. This is our research, and the members are listed below. In this picture, the point date in the black rectangle represents a pig's scapula scanned by micro-CT, and the two small ones are the real structures in different layers. In the screw path drilling, we often penetrate the outer cortical bone and make the drilling bit stop when it reaches the key point. However, the penetration rate is not good enough based on image and force. Furthermore, the penetration may hurt some important tissues, so we should study more methods to improve the accuracy. The left picture shows the original signals, but it's difficult for us to tell the states in real time. And according to the right picture, we select an effective frequency band to reduce the interference caused by human voice, the use of instruments, and so on. Then we come up with two algorithms, the exponential mean amplitude and the Hurst exponent. The former one represents the audio signal's intensity in the target frequency band, while the latter one represents its stability. Here is the result of EMA method. And this one is the HE method. Both of them can recognize the key points by setting the relative threshold. In our experiment, we use these two methods for state recognition. This is our experiment platform, and the states are divided into 4 parts. Among them, the most important part is the inner cortical layer state. And here is the video. For showing the entire process, we set a higher threshold than normal. Now, drilling bit is running. And now it stopped. This is the experimental results. The success rate in fresh bone group is much higher than in others. We hope this study will help the doctor and the patients one day. Thank you.
Good morning. My name is Rajni Patel, and I'm presenting this paper on behalf of my former doctoral student, Martha Koshnam, who couldn't be here because of visa problems. The talk is on estimating contact force for steerable ablation catheters based on shape analysis. The problem we deal with is with the technology used for a treatment for cardiac arrhythmia, in particular for atrial fibrillation, which is the most common type of serious arrhythmia. It involves very fast and irregular contraction of the atria, which can result in serious problems such as blood clots that could lead to stroke. So cardiac ablation is a mechanism to remove or terminate faulty electrical pathways from the sections of the heart by ablation using electrical energy. And the ablation is performed using an ablation catheter, which is inserted into the atrium through the vasculature. This is done under image guidance by using X-ray fluoroscopy to visualize the catheter and the guide wires inside the vasculature. The success of the ablation procedure depends on the accurate positioning of the catheter tip and the consistent and correct contact force that should be applied between the catheter tip and the cardiac tissue, which is of the order of about 20 to 30 gram force. Several technologies have come on the market in recent years that use catheters equipped with force sensors, but these are quite expensive and require equipment and specialized catheters. The sensorized catheters are also single use. For conventional catheters, no contact force information is available, and our work is focused on developing methods for estimating the force of contact between a catheter tip and cardiac tissue. This is done by observing the shape of the catheter's deflectable distal shaft when the tip is in contact with tissue. We have developed a number of models which have been evaluated through experiments with conventional catheters. And these figures show how different contact forces change the shape of the deflectable shaft. We analyzed how the curvature changes as a result of the applied force. And based on the results of the curvature analysis, we found that it's sufficient to monitor the curvature of a certain section of the catheter shaft. In our study, we were able to define an index to determine the range of contact force. Our experimental results indicate that we can correctly estimate the range of contact force in more than about 80% of the cases. Work is in progress to improve upon this result. So if you want to discuss more about this, please come to the lecture session. Thank you.
Good morning. My name is Ryan Murphy. I'm with the Johns Hopkins Applied Physics Lab and Johns Hopkins University. I'm going to talk about predicting kinematic configuration from string length for a stank-like manipulator. This manipulator doesn't exhibit constant curvature bending, and that's one of the problems that we found compared to some of the other literature, is that without this constant curvature bending, it's a little bit hard to predict what the configuration will be. So we've developed a method to do that. The manipulator that we have is a single plane bending manipulator composed of nested nitinol tubes. So we can consider either C or S-shaped bends with this type of manipulator. It's 35 millimeters long and has a 6 millimeter diameter. Actuation is pull-pull cable, so we have cables running along either side. And as I mentioned, we know that this manipulator demonstrates non-constant curvature bending, and so what we're looking to do is, given the actuation position, given the actuator position, can we predict what the tip position and what the underlying configuration of this manipulator is? Now, if you're interested, I have this manipulator with me today, and you can come by the talk and see it. So preliminarily, we've modeled our manipulator kinematics as a series of 27 rigidly connected pin joints. This is just a geometric definition. We have limited bend angle because as the manipulator bends, it's going to come in contact with itself. And then we've just defined a series of notch points along the length of the manipulator that we've dubbed P. We've shown that this does effectively model manipulator configuration, and so that's good. The manipulator modeling that we have here is a two-step modeling procedure. So we're taking in string length, basically actuator position, and then we're going to predict an effector position. We've modeled this as a Bernstein basis polynomial, a 7th order Bernstein basis polynomial. That predicts the X position. Then we use that information to predict the Z position. So once we know this tip position relative to the base, we can effectively estimate the manipulator configuration. This estimation is done using an energy minimization approach. So we assume constant torsion, or excuse me, we assume torsional springs with constant stiffness, and then we find the minimum energy required to actually achieve that configuration. We have an experimental setup here that we've created an actuation unit for our manipulator. We have an overhead camera. This camera is what we use to define our ground truth for the images. So you can see an example camera image there. We have an image registration procedure. It's a piecewise rigid deformation. From this, we can actually identify the manipulator configuration, use that as our ground truth to compare our results to. The results actually worked out pretty well. there were comparable tip position errors among the test and training data sets. So what we've done is we fit this model from the test data set and use it on a training data set. Sub-millimeter accuracy here, which is very, very nice for tip position. And the average molecular configuration errors is very good as well. Throughout this, we saw 12 outliers with a max error greater than 2.5 millimeters. And if you come to the session today, I'll be happy to tell you more about it. Thanks so much.
Good morning, everyone. I'm Paulo Cabras, and I'm going to present the work I've carried out with my colleague at the University of Strasbourg concerning techniques to measure the position of actuated instruments in flexible endoscopic surgery. In robotic no-scar surgery, the instruments are inserted in the channel of a flexible guide equipped with an endoscopic camera, providing a 3 degrees of freedom mechanical system with translation and rotation in the channel and deflection. The system, which was robotized in our lab, can be used to carry out endoluminal surgery, single port, or even the so-called NOTES, natural orifice transluminal endoscopic surgery. For control application, the special configuration of the flexible instrument is fundamental. So in this work, we propose to estimate the position of the instruments of the anubiscope using solely the endoscopic images with the help of 3 markers attached to the instruments. The main issue when dealing with this approach is the knowledge of a precise kinematic model that is not always easily obtainable. So to cope with this, we decided to investigate the potentiality of a learning approach with respect to a more common model-based algorithm. In learning approach, we don't need any model, so the system is considered as a black box where we want to compute actually the relationship between the input and the output data, so which are, in our case, the image future point vector and the instrument 3D position. We opted for a radial basis function nectar with Gaussian kernels, which allows to approximate a function as a weighted sum of Gaussian. The training set is built with several samples composed by the coordinates of the 3 centroids of the yellow markers in the image, and the corresponding 3D space position of the instrument tip, which was gathered with the electromagnetic sensor position on the tip. The training is divided into 2 steps. Firstly, unsupervised learning to determine the center and the shape of the Gaussian, and then a supervised learning to have the best linear combination of the kernels. On the other hand, as a term of comparison, we decided to use a model-based approach using the camera model and the camera-to-end effector kinematic chain to retrieve the configuration of the robot. What we can do is create a virtual image from the configuration of the robot and compare this with the actual image, and so define a cost function based on the future of the instrument. Test shows that a better average error values using learning approach than other model, either using the precise model or improved version. If you want to know more, please come and visit me.
I'm Shinji Tanaka from the University of Tokyo in Japan. The topic is robust forceps tracking using online calibration hand-eye coordination for microsurgical robotic system. In microsurgery, the surgeon has to perform very fine tasks such as anastomosis of fine blood vessels. And we have developed a microsurgical robotic system and succeeded in anastomosis of 0.3 millimeter blood vessels. And our next challenge is more intelligent control, such as surgical automation, and therefore autonomous recognition of surgical process and environment is required. As one of such techniques, we developed forceps tracking algorithm which uses visual and kinematic information for robustness. In this previous research, we assumed that the hand-eye coordination between the robot and the microscope is assumed to be constant, but this assumption is invalid because the microscope is repositioned frequently during the surgery. So in this work, we developed a tracking algorithm which considers the repositioning of the surgical microscope. This is the overview of the algorithm. In the preoperative process, the color model and the counter model are constructed. And intraoperative process, the forceps is extracted from the stereomicroscopic image using the color model, and the edge is detected from the extracted forceps image. Then the counter model are compared with the detected edge, and the state of the forceps are estimated using the particle filter. The kinematic information is incorporated into the tracking through the forward kinematics and hand-eye coordination. Then the hand-eye coordination is only recalibrated to cancel the repositioning of the microscope using the feedback from the tracking result and the sensory data from the robot. And we tested our algorithm using the video of the needle placement task, and we confirmed that the tracking was almost successful, and the offset error caused by the repositioning of the microscope was cancelled in the proposed method. Thank you for your attention. I'm looking forward to discussing in the interactive session.
Hello to everyone. Professor Dupont, Dr. Fulful, and myself are with Boston Children's Hospital, and our paper is titled MRI-powered closed-loop control for multiple magnetic capsules. Controlling particles inside the human body has many potential applications. Up until now, there have been papers appeared that deal with control of nano and micro robots as well as individual robots. However, we are interested in controlling independently millimeter scale magnetic robots inside fluid-filled body lumens. These are of particular medical interest, such as, for example, they can be used for targeted drug delivery in places where conventional procedures cannot reach. Our goal is to use a clinical MRI scanner that can be available in any hospital for power and tracking of the capsules, and in order to achieve closed-loop control for multiple capsules in the presence of constraints and disturbances. The use of the clinical MRI scanner introduces some difficulties. This is that the magnetic field of the MRI applies uniformly to all the group of the capsules, which makes the independent control of each capsule a challenging task. And the actuation and the tracking mode of the MRI is not simultaneous, but is interleaved, which causes additional problems with respect to closed-loop systems, with standard closed-loop systems, such as it introduces delays. In order to address this problem, first we use different dynamic parameters for each particle in order to differentiate their motion. And secondly, we use a constrained model predictive control framework to explicitly account for delays, constraints, and disturbances. After some intense math, we have achieved to design a robustly stable controller. We have proven that the closed-loop system is input-to-state stable with respect to disturbances. And we have efficiently answered when the MRI should be on actuation versus tracking mode. Thank you. We'll be at the interactive session for further questions.
I'm Toshiaki Tsuji from Saitama University. I will talk about rehabilitation database utilization. First, it's about our motivation. Can robots substitute therapists in clinic? Although many people believe so, therapists and robot engineers involved with rehab robots know that there are so many issues to substitute therapists' tasks. So the answer from the field side is so far no. Most of the therapists think that robots are too expensive, bulky, and stupid for practical use. On the other hand, the merit of robots is that robots can automatically have accurate sensing. This video is an example of muscle force visualization using augmented reality technique. This is something therapists cannot do by themselves. So this study tries to utilize the accurate sensor data for new services. So upper limb training robot using pneumatic artificial muscles are used in this study. The rough property is as follows. A setup of mechanical stiffness by antagonistically driven muscles, An accurate guidance control with the setup of stiffness ellipse. Training enhanced by visualization based on computer graphics. So the first utilization of training data is for design of joystick for rehabilitation robot. The mechanical setup of the joystick for control of exercise therapy is optimized through experimental data. We compared the results of 3 different stiffness of the joystick. This is the video of the experiment. The subject moves the affected side so that it follows the target. It is assisted by robot controlled by the joystick in the healthy side. The left figure on the, is on the tracking error. The tracking performance in traveling direction was good with a certain stiffness. So that's a best stiffness condition. This is an easily guessed fact. An interesting fact newly known here is that the error in cross direction is better if the joystick has lower stiffness. So the database indicates that the effect of stiffness to control performance is different in each direction. So we have some results on comparing vertical and horizontal displays for low cognitive capacity people, but for time issue, this is skipped and it is shown in the interactive session. So this is all the presentation. More detailed information will be explained in the interactive session. Thank you.
Good morning. My name is Ki-ho Jang. I'm going to talk to you today about the work that I have done with my colleagues in Hanyang University using EMG signals to control electron wheelchair with variable speed. As shown below figures, U-turn of electronic wheelchair requires faster rotational speed than S-turn zone. To control electron wheelchair in the varying environment, we have to extract 2 informations, such as which muscles are activated and each amplitude levels from EMG signals. 2 EMG signals measured from right and left sides of zygomaticus, major muscles. Since low EMG signals are very noisy, we extract an envelope of the low EMG signals to reflect the moving average activity. The simplest method is RMS operation. During voluntary muscle contraction, both RMS signals have different amplitude levels. Thus, we utilize the normalization method to make the amplitude levels equal. A summation of product operation is utilized to indicate simultaneous activation of both muscles. Acceleration and de-acceleration commands are generated after applying threshold operation to the SPW signal. The acceleration signal inevitably has a cut part due to threshold operation. This part should be removed in order not to affect on acceleration of the electron wheelchair. Desired velocities are generated by using linear combinations of the input signals. Using a wheelchair kinematics, or wheelchair controller provides rotational speeds over 2 wheels from desired velocities. To show effectiveness of the proposed method, we choose an obstacle avoidance task in the experiment. First plot in the below show right and left normalized RMS signals as input of a proposed method. Middle and last ones show respectively linear and angular velocities generated by using the input signals. I'd love to talk more detail in the interactive section, and thank you for your attention.
Okay, good morning, ladies and gentlemen. I'm Wei Minian from National Taiwan University. Today I'm glad to share you about a recent research about the dynamic toe gain adjustment method for frozen shoulder rehabilitation. Frozen shoulder, also known as adhesive capsulitis, is a functional disorder that the sac of the ligament surrounding the shoulder joint will be swelled and stiffened, which means the patient's mobility is restricted, so the range of motion is smaller than a normal person can do. And sometimes the pain will occur during their exercise. And there are about 2 to 5% of the general population suffer from this disorder. However, this topic is rarely discovered in the rehabilitation robotics. So our motivation is to provide a method to evaluate the stiffness and give a sufficient support when patients are needed. Therefore, based on the exponential relationship between the human joint torque and the joint angle, we define our stiffness as a SI and the human mobility as a control authority, CI. Furthermore, we use the exponential function to define our stiffness model, SIM. So our strategy for treatment can be shown in this diagram. We obtain a patient's torque in each time interval. And once we attain such a torque, we can calculate the stiffness and the control authority. And we further use the stiffness model to generate our gain value, which can offer the assistance force when the patient lack of power to finish their exercise. So here's our experimental result. We compare the normal and the abnormal group. And we can see in the both groups, their stiffness curve appear the exponential relationship just match to the property of the human joint torque do. And our gain function will be offered as far as near to the limit angle of the subject. So to sum up, in this research, we propose a stiffening model and a dynamic torque gain function to offer the assistance force to the patient, and which will provide a safer and more effective and a quantifiable rehabilitation exercise for the frozen shoulder patient. And more detail could be found me at the interaction session 10, and hope to see me soon. Thank you very much.
Once again, I'm here to talk on behalf of my doctoral student who couldn't be here because of visa problems. The topic is involuntary movement during haptic-enabled robotic rehabilitation. Currently, there are more than 7 million people in the US who have survived a stroke, and there are about 1 million people in the US who are living with Parkinson's disease. This is likely to increase significantly as the population ages. And it is very likely also that a significant proportion of the stroke survivors will have Parkinson's disease and vice versa. So this creates a problem for the use of conventional robotic-based rehab technologies for these patients. Robotics-based post-stroke rehabilitation technologies have been shown to be very useful for rehabilitation and have been well documented. So the targeted population for this work are people who have had stroke and who have both Parkinson's disease like tremor and paralysis, or Parkinson's disease patients who suffer from slowness, coordination, and deficit in tremor. Haptics-enabled robotic rehabilitation is widely used for post-stroke patients, but those without tremor, and shows many advantages over conventional therapy. The haptic device is connected to a virtual environment, and the system provides some assistive-resistive forces to administer the therapy. The project deals with using robotic and rehab technologies for targeted populations of this study. And these patients do not have any control over the tremor. We consider assistive therapy where the therapist provides motions to assist the patient. This is clearly not passive, so the patient with a tremor, it is possible that the assistance could make the tremor more larger. And we deal with this tremor amplification issue, and the experimental setup is shown here. A typical case is the figure on the right. The black line is the movement incorporating involuntary tremor, and the red line is the extracted voluntary motion. Our solution is this hybrid-enabled architecture shown here. The architecture separates the voluntary and involuntary components of the patient's movements and uses a novel adaptive filter. This provides a strategy that resists the higher frequency components of the tremor and assists the lower frequency movements. So if you'd like to discuss this further, please come to the interactive session. Thank you. Okay, this is another problem with the visa, so I'm talking on behalf of my doctoral student, who is the first author on this paper. And the task that she's looking at is work on a framework for supervised robotics-assisted mirror rehabilitation therapy. So every year, more than 15 million people worldwide suffer from stroke, and nearly 6 million die from it, and the rest have some form of impairment. So stroke is the second leading cause of disability after dementia, making it a major cause of serious impairment. This indicates a growing need for rehabilitation therapy, of which mirror therapy is one possible approach. So mirror therapy is a rehab approach mainly effective for patients with hemiparesis. This is one-sided impairment which affects almost 80% of stroke survivors. It's conventionally done with mirrors, of course, but we are proposing a teleoperation format. The robotics assistance provides the patient with an active mirror-symmetric movement. The impaired limb attempts to mirror the movement made by the functional limb, or the unimpaired limb. The existing robotic frameworks offer several advantages, but do not involve a therapist in the loop. So we propose the therapist in the loop framework using concepts from dual-user teleoperation. The therapist and the patient's functional limb each have partial control over the patient's impaired limb. The therapist provides desired trajectories for both limbs. So the patient can modify the trajectories using the functional limb if he or she feels any discomfort. The system provides the therapist with haptic feedback as well from the patient's impaired limb, so the therapist is aware of what the patient is feeling and how the patient is moving. And the guidance virtual fixture is available for impaired limb for an assist as needed therapy. Our system offers the advantages provided by conventional mirror therapy, but also benefits from the knowledge and expertise of the therapist in the loop. So if you wish to discuss this further, please drop by the interactive session. Thank you.
Hi, my name is Tomoyuki Noda from Department of Brain-Robot Interface in ATR Computational Neuroscience Labs. Today, I'll talk about our hardware development of upper limb exoskeleton powered via hybrid approach. The goal of the hardware development is to build a lightweight upper extremity exoskeleton robot to be utilized in this kind of rehabilitation scene or supporting daily life for physically challenging people. And we are planning in the future combined with BMI approach. To support human limbs, torque generation must be sustainable and large, fast. And at the same time, the joint has to be backdrivable with inherent compliance. These claims seem contradictory if you only use one single principal actuator. But as we and another researchers has pointed out, hybrid approach makes it possible. In this demo, the PM pneumatic axial muscle torque force and the small motor torque generate 10 kilogram gravity compensation task. As a result, I can move up and down by only using my one finger. That is possible because different torque bandwidth is covered by two torque sources. PM covers sustainable and large torque, but it's slow. So small motor covers short but precise and quick torque, as this figure shows. This paper proposed antagonistic PM forces transmitted via ball and cables, besides small motor mechanically coupled close to the joint. The good things of this design is making this joint arm backdrivable with sustainable large torque generation with compact joint. As you see in the finite torque control off, that is very backdrivable. And this design makes this prototype arm, its current weight is 5 kilograms, and torque is more than 50 Newton meter is possible. And this paper's contribution is design and modeling. So we are also recruiting people on robotic learning and lower limb exoskeleton control and software engineering. So please join us. And I brought some of the PM demonstration device, so you can touch in the interactive session. See you.
My presentation is about keyboard-driven robot for 3-degree freedom rest and forearm motion training. And millions of people suffer from motor abilities to perform activities of daily living. And most of daily operations need dexterous operation of our upper extremity. Robot-aided rehabilitation using keyboard-driven robot can be low cost and be customized to different size and different functional training. So our target is to develop a keyboard-driven robotic device focusing on dexterous functional training for arm. And this is our system. It's mainly a keyboard-driven parallel mechanism, and it includes two platforms: fixed platform and a moving platform. The fixed platform is fixed on the arm, and the moving platform is held by the hand. We use 4 distributed cables to drive the 3-degree freedom motion. And because of its cable-driven design, it can be cost-effective, low weight, and low moving inertia, and easy to reconfigure to different needs. In order to provide arbitrary torques on the arbitrary required torques on arm, and so we make the range closure workspace analysis. This is a result described in joint angles. Because the arm is involved in the system, so we provide this algorithm to identify the arm length. And from the theoretical result, we can say this algorithm is fast, convergent, and robust. It provides possibility to make a parameter adaptive control. And this is our experiment setup. The hardware system is mainly based on DSP and FPGA. And the human interface is we use Windows Precision Foundation. For the sensors, we use the orientation sensor to measure the orientation of the moving platform. Oh, yeah. If you have any questions, we can meet at the salon. Thank you.
I'm Eric Shearer, and I'm from Cleveland State University, and I'm going to talk to you about the work that I've done with my colleagues at Northwestern and Case Western and using a robot to aid in identifying the inverse dynamics of a human arm. This is a person I work with in Cleveland. 20 years ago, she had a gunshot wound that left her paralyzed from the neck down, and we want to restore her ability to feed herself, to comb her hair, to open doors, and other tasks that require reaching. To restore these capabilities, she has an implanted functional electrical stimulation system. We're able to send current to muscles and nerves in her shoulder and arm, causing the muscles to contract and move her arm. And the overarching goal here is to be able to control a human arm in much the same way we control a robot arm. So given a desired trajectory and joint space, first, determine the torques required to move along that trajectory, and second, figure out which muscles to stimulate to produce those torques. And it's the first part, the identifying the inverse dynamics of the arm, that's the subject of this talk. So we gather data to identify the inverse dynamics. by having a robot move her hand along various smooth reaching trajectories. And while the robot's moving, a force sensor is sensing the force to drive the hand along the trajectories, while a motion capture system measures the motion of the shoulder and elbow joints. So given that we know the measured force, F sub r, we can compute the equivalent torque about the shoulder and elbow joints. And then using that torque vector as the output and the shoulder and elbow joint positions, velocities, and accelerations as the inputs, we use Gaussian process regression to predict the torques required to drive the arm along any given trajectory. So knowing these, the inverse dynamics and the dynamics of torque generation by the muscles, we can define a trajectory for the hand to move along and then stimulate the muscles to move along that trajectory. And this video is showing the arm moving under functional electrical stimulation control. And this is the first demonstration of a decentralized control of a multi-joint functional electrical stimulation system for arbitrary goals on a human. If you have questions, I'd love to see you during the interactive session. Thanks.
Hello, my name is Purya Talibifat from University of British Columbia, and I'll be presenting a risk assessment infrastructure for powerful wheelchair motion commands without full sensor coverage. This is part of the Campbell project, whose aim is to develop a collaborative controlled powered wheelchair for older adults with cognitive impairment. In a previous study, we identified that individuals would make too early or too sharp of a turn. The wheelchair was unable to intervene because of the limited field of view of its sensors, as illustrated here on the left. The doorway moves out of the field of view before the user even gets close to the doorway. Of course, it would be easy to correct and avoid such scenarios if we could place sensors all around the chair. However, that would be not practical for financial and a host of other reasons. Instead, we wanted to see whether we could identify the collision risk in this scenario with only a single cheap, almost invisible RGBD camera sensor that's mounted underneath the wheelchair. We believe that the user studies will be needed to identify the appropriate risk metric. Consequently, in this work, we set out to design an infrastructure on which a variety of risk metrics could be evaluated. Our infrastructure consists of an egocentric occupancy map, which follows a standard probabilistic map of the scheme. Since the chair is always centered in the map, there is no need for localization, and sensor updates are pretty cheap. This is similar to vector field histograms, except instead of distance to the nearest obstacle, it keeps an entire probability density in each direction. The second element of the infrastructure is a model for the motion of the chair. Direct modeling and control of commercial wheelchairs is not possible because of the interfaces are trademarked. We can override the joystick, but the mapping between the joystick and motion is nonlinear and dynamic. Because we do not yet know the appropriate risk metric, we use a strawman proposal of greatest log odds of collision to exercise our infrastructure. We designed experiments based on the cornering scenario. These are time series plots of the reported risk from two safe and two unsafe trajectories. As you can see, as the chair as the system starts, the risk is moderate because map is unknown. As the chair drives down the corridor in the free space, the system reports very low risk. As cornering begins, the risk rises again. In the safest case, top left plot, the risk only rises to moderate levels, while the least safe case, bottom left plot, the risk rises dramatically. We also performed a longer free navigation experiment. This is a pre-computed map showing the trajectory. As you can see, high levels of risk are reported when the chair gets too close to an obstacle that it's facing, and also when it tries to back up into an obstacle, although it's not seeing it. Thank you.
Hello to everybody. My name is Matteo Malosio. I would like to introduce you to the lean arm. Lean arm is a variable stiffness actuated device for the rehabilitation of the upper limb. And let's see, it's a short story. If we can group the rehabilitation devices into two main groups. Devices optimized for the clinics, which are usually very smart, but they are quite expensive, with many degrees of freedom usually. And the ones developed for the house, which are quite cheap but usually are unactuated or gravity compensated. The linear arm has been designed and optimized to take the most of both these categories. How does it work? As many of you know, if we have two motors with a compliance in series, we can control both the equilibrium position and the stiffness of a mass. And why to use variable stiffness actuation for rehabilitation devices? Because usually it's quite useful to control also the stiffness of the handle and not only the position of the handle for the end effector of a rehabilitation device. It's very useful to control also the force exchange by the patient. And force estimation is quite cheap for such devices and also simple. Safety is very important, and these devices are intrinsically compliant, so it's a good point from this point of view. And also, rehabilitation devices usually doesn't require so much precision, so variable stiffness actuation, this is one of the drawbacks, but not in this case, probably. How does it work? We have two antagonistic motors connected to the handle by two groups of very cheap and commercial springs. We can compute both the stiffness and the applied force at the handle according to their configurations. And what about the prototype? We optimize the prototype to be as low cost as possible, both from a mechanical and electrical point of view. Sorry. The mechanical components have been optimized to be 3D printed by very low cost printer. And the electronics is completely based on the Arduino controller for the low level. And the software, we developed a two-level software. So there is the Arduino controller on the lower part, which is a multitasking and real-time system. We use the CBOS real-time layer. And on the upper part, we have a Python program. All the devices are static on the Python layer, so it's completely programmable by Python script. So if you are interested in it, I would like to show you directly on live, because we have a live demo downstairs. Thank you very much.